one space and one time dimension. That's 1 plus 1. And we started with an action, which was dx, integral dx dt, half of the kinetic energy term minus the spring potential energy minus 2 V phi. V phi is the potential, gravitational potential. Where V phi was alpha by beta 1 minus cosine beta phi, which also we wrote as 2 alpha m beta by beta square sine square beta phi by 2, and alpha beta we called m square. We also realized that we can write twice V phi as a derivative of some function of phi u, prime being derivative with phi square, where u phi prime is this object 2m by beta sine beta phi by 2, and u phi, if you integrate that, is minus 4m by beta square cosine beta phi by 2. And then we wrote the corresponding Hamiltonian for this theory. H is dx, integral dx, half from minus infinity to plus infinity of the kinetic energy term plus potential energy plus 2d of phi. And V of phi, if we draw its profile, V of phi as a function of phi it's a cosine curve zero, 2 pi, 4 pi, minus 2 pi, minus 4 pi. So the minima of the potential V phi are at points phi or beta phi equal to n 2n pi, where n is 0 plus minus 1 plus minus 2. So these are the classical ground states. Infinitely many classical ground states where for all these values V phi is 0 and it's minimum of V phi. So we have classically many degenerate ground states. Degenerate means they have the same potential value. So each one of them is classically as good as any other as a ground state. So there are infinitely many ground states, and each one of them is as good as any other. And in the model that the cloth line and peg model, the ground state is that when all the pegs are vertically downwards, all pegs vertically downwards. and this is ground states. Then we ask the question, are there other static configurations? Are there any other static configurations? Which solve the corresponding equation of motion. We didn't, last time I wrote the equation of motion also. Yeah. For this theory, for such static configurations, the mass would be given. We are working in C equal to 1 units, be given by the Hamiltonian. Plus 2v, and 2v was u prime of phi square. And this, we said, we will rewrite it in a way as half integral dx of d phi x plus minus u prime phi whole square. And then from this whole square, in order to get this, subtract the term, which is twice d phi d by x of u prime phi. And this will we rewrite as half dx of d phi by dx plus minus u prime phi square, and this integral plus minus we call it t. Right? Let me write down t explicitly. T is dx of d phi dx u prime of phi minus infinity to plus infinity. From here, one can read off clearly, because this is a complete square, so this is a positive quantity, that tells me that this mass of such configurations, static configurations, is bounded by value t, which is m is greater than or equal to plus minus t. And the equality is holds when this object is 0. So equality when n equal to plus minus t, when the the solutions of this equation. Okay. Now let's look at this object t that integral minus infinity to plus infinity of d phi dx u prime of phi. This I can write as integral of d phi of u prime of phi. From with the lower value of phi, value is phi of at minus infinity and phi at plus infinity. And therefore, it's given by u phi, with value at x equal to plus infinity minus the value at x equal to minus infinity. And now if I put u phi there, u phi was minus 4m by beta, not cosine, cosine beta phi by 2 at phi plus infinity and phi minus infinity. Now let me think of a configuration which has the nice property, a configuration which, if I plot it as beta phi as a function of x, at x minus infinity it is 0, and x plus infinity, this is 2 pi. A phi which has this property, that at beta phi at minus infinity is 0 and at plus infinity is 2 pi, is a particular configuration. Or another configuration that at minus infinity the configuration is 2 pi and at plus infinity it's 0. So this is 2 pi, this is 0. Now if I calculate this t object for this configuration, it gives me this object at plus infinity, beta phi at plus infinity is 2 pi, which means beta pi by 2, at plus infinity is pi, so cosine of pi, minus cosine of phi at minus infinity, which is 0. So cosine pi minus cosine 0 is 2, is minus 2. So that gives me 8 right here, 8m by, did I get beta right? This is beta square here, right? And similarly now if I calculate t for this object from the same formula, cosine plus infinity is 0 and cosine at x minus infinity is 2 pi by 2, that's cosine pi. So that gives me answer minus 8m by beta square. We'll give a name to these configurations. These two configurations that we give a name to them and call the first one soliton and call the second one anti-soliton. Now in order to understand the properties of what we have called soliton and an anti-soliton, let's introduce a current, J mu defined by beta by 2 pi epsilon mu nu d nu phi. Just construct an object like this, which is beta by 2 pi epsilon mu nu. Epsilon mu nu is antisymmetric 2 symbol. It means when mu and nu are equal, it is 0, and when mu and nu are t and x, it's 1, and it's an antisymmetric object in indices mu and nu. And if this is some current, it has a very interesting property that this current is conserved. Divergence, 4 divergence of this current is 0. It's a conserved current. But what's nice about it that this, we have given a name to this object current whose divergence is 0, but we know objects and we call them currents whose divergences are 0 from Noether's prescription of finding out conserved currents associated with symmetries. But when we study the conservation of Noether currents, though conservation of those currents is valid by using equations of motion. I think we calculated one exercise earlier, did we? In some context. So for Noether currents and this current are different. In what way are they different? Is Noether current is conserved by using equation of motion. This object is conserved without any use of equation. It is conserved simply because there is an epsilon mu nu sitting here which is antisymmetric. So derivative of this is epsilon mu nu, 2 derivatives. And 2 derivatives are symmetric on functions which are reasonably well defined, and therefore that is 0. So this is a current which is conserved irrespective of whether phi satisfies equation of motion or not. Another nice property of this current is, so this current is conserved without equations of motion, without invoking equations of motion. So this current does not represent any symmetry or a continuous symmetry of the theory, because that's what Noether currents represent. And like in any other current, if I define a charge, which is what I would call it Q, which is this space integral of the 0th component of the current from minus infinity to plus infinity, that object here, if you work it out, is beta by 2 pi dx of d phi dx minus infinity to plus infinity. Okay. 0th component is the time component. 0 means time here. So that is 0, and therefore first component, which is x, so it is d phi of dx, an integral. That is beta by 2 pi value of phi at plus infinity minus value of phi at minus infinity. And for those 2 configurations that I constructed, beta phi at minus infinity is 0 and beta phi at plus infinity is 2 pi. So that is plus 1. And for the second configuration, there, where beta phi at plus infinity is 0 and at minus infinity is 2 pi, this object is minus 1 for soliton and anti-soliton. And therefore, this quantity T that I had constructed here, this quantity T is 8 m by beta square times q for these two configurations, q plus 1 for soliton and q minus 1 for soliton. So essentially, up to the normalization of 8 m by beta square, T is the soliton number. Okay. One more thing. Notice this current that I have defined here, it is a total divergence on its own, because I can write this as d nu of beta by 2 pi epsilon mu nu So that's another property of such currents, their total divergences. Currents which are total divergences and are conserved without using equations of motion, such currents are called topological currents. And Q is a topological charge. Why the word topological? Because it measures topological properties of these kinds of configurations. It measures only the boundary values of these configurations. What structure they have inside. I mean, instead of this, it could be like this, it could be like this, and some other configuration. It does not see the detailed structure of the configuration, it sees only the boundary values of the configurations. And in that sense, this configuration is different from this topologically. Okay? So it measures topological properties of the configurations. So that's why the name topological charge or topological current. Now let's try to work out what is a configuration of this type, these two types, which solves the equations of motion. Solves the equation of motion means which gives you a minimum of the Hamiltonian, and this is a positive quantity. So minimum means that this object is 0. So configurations which solve the equations of motion and have this property means that they have the boundary properties that they go to 0 on one side in this curve and 2 pi on the other and 2 pi on this side and 0 on this. So configurations with q equal to plus minus 1, which also solve equations of motion. Configurations which solve equations of motion are also the extremum of the Hamiltonian. So which means they solve d phi by dx plus minus u prime phi 0. And for these configuration, the corresponding mass is For configuration with the minus sign, it is plus t. For plus sign, it is minus t, but minus t and the t for the second configuration is negative, so minus t is positive. Now let me put what u phi was. U phi, we wrote what u phi is. Rewrite this equation as d phi u phi plus minus dx. And solve it by integrating it. So we solve this equation by rewriting it as d phi divided by u prime phi plus minus dx and integrate it. And what was u prime phi? Somewhere we wrote it earlier. It's 2m by beta sine, right? Sine beta phi by 2. So what do we have here? We have beta by 2m integral d phi by sine beta phi by 2 is plus minus dx. Now this is just easy integral to do, and I'll leave that as an exercise. Do this integral, and the solution of this thing is given by tangent beta phi by 4 is plus minus exponential plus minus mx. Integrate it and solve it. And that's the solution. Or beta phi by 4 is tan inverse of exponential plus minus mx. Now notice, for the plus and the minus signs, two signs, there are two solutions. And if you take the plus sign, then beta phi at minus infinity, take the plus sign, x minus infinity is e to the minus infinity. E to the minus infinity is 0. Tan inverse 0 is and beta phi at plus infinity with the upper sign is exponential infinity. Exponential infinity is infinity. Tan inverse of infinity is pi by 2. So beta by 4 is pi by 2. So with the upper sign here, we have a solution with the profile given by this. So that is the soliton. And for the lower sign, beta phi minus infinity, x minus infinity with the minus sign here is exponential infinity, and exponential infinity is tangent inverse exponential infinity is pi by 2, so that's 2 pi. So we have found now two configurations of this theory given by this configuration, with these solutions, which have that kind of a behavior, that at x minus infinity they sit in one of the ground states, because beta phi equal to 0 is a ground state, and x plus infinity sit in the other ground state, because beta phi equal to 2 pi is the other ground state of the theory. So at the extreme points they are in the ground states, in between they have structure. And for the mass for these objects, let me write it again, for these two cases is, both of these cases is the same mass, is, because q is plus minus 1. So these configurations have the same mass but different boundary behavior. Now if I want to visualize this in my cloth and peg model, what do these configurations look like? Let me try to draw it for you. So soliton in the cloth peg model, pegs model. We have an infinitely long cloth line, and at x minus infinity the configuration is sitting at 2 pi. The first one is sitting at 0. So the peg is vertically downwards at minus infinity. Then as we go away from minus infinity, come towards 0, then the peg, which was like this, starts tilting upwards. So it tilts. I have drawn it like this, but what I mean is like this. And at another point it's little more, another point is little more, at another point is little more, and finally at some point it's up, it's above the line. And then, so, and let me draw it here, and then it is above the line. So profile is like this. And then here above the line, this was above the line, and this is now, line is behind. It's the pegs are above the line now. So the peg has taken a complete 2 pi rotation and come back to this position. So that's what a soliton is. And anti-soliton, minus infinity 2 pi downwards, gap here. So what it is that it's going like this underneath. So that's why I draw the line above here. So when it turns around there, it's going inside the blackboard, and then turning like this, and then coming over here, and then coming over the line here. So that's an anti-soliton.
I thought that maybe we could visualize that better by tilting the lines in the opposite direction.
Or maybe all right. But is that clear? See here, the pegs are like this, then they start moving up, then this, and then they go around underneath, and then come down here. And in this case, they go like this, they go from the other side underneath, and come above, and then above the cloth line, like this. So now we understand what these configurations are. We focus on what I have said already and repeat it, is that there is an associated conserved topological current with these configurations. And that topological current is different from Noether conserved current. Topological conserved current So topological conserved current versus Noether's current. What are the properties that distinguish them? To remind ourselves, what did we say? The topological current we had is 1 by 2 pi or beta by 2 pi exponential E mu nu d nu phi. And the corresponding charge, and this was conserved, and the corresponding charge was q integral dx of g0 minus infinity, which is dx of d phi by dx. For ground states, this charge q is 0 because phi is 0 or 2 pi everywhere. Pi, 2 pi, 4 pi, beta phi. And for solitons, q is +1. For anti-soliton, q is -1. Now if I draw two columns, topological current and Noether current, then topological currents have the property conserved independent of equations of motion. Noether current conserved only for those configurations which satisfy equations of motion. Of course, this also is conserved for configurations that satisfy equations of motion. That's true, because if it's conserved for any configuration, it's also those configurations which solve equations of motion. Second property, J0 here, the corresponding 0th component of the current, contains canonical momenta of the theory. So if you have a set of fields, some set of fields phi, and there are stated canonical momenta, J0 contains canonical momenta. And if J0 contains canonical momenta, then J0 and fields, Poisson brackets, are non-zero. And what they do, what the J0 does, the charge density corresponding to these conserved currents, J0 is the charge density corresponding to these currents, is that it changes the fields. And it changes the fields by some amounts which are exactly the symmetry transformations of the associated symmetry with this conserved current. So J0 generates the symmetry. J0s are generators of symmetry. The stated symmetry. On the other hand, topological current densities do not contain any momenta. Therefore, J0 Poisson brackets with the fields is 0. So therefore, these J0s don't generate any continuous symmetry. They only probe the global symmetries, topological symmetries. So do not generate any continuous symmetry. Third property, J0 is always a spatial divergence. And in this case that we were here, considering in the here, we are in 1 plus 1 dimensions, so space dimension is only 1. d phi by dx is a divergence in 1 dimension. If you have such objects in higher dimensions, then you will have space divergence. Yes?
J0 will have a d phi by dt, right? So cannot we change the d phi by dt in terms of some pi, some
Where is dt? Which J0 are you talking about? The J0 of the topological current or J0 of the Noether current?
J0 e u u d u phi. So this current. Yes.
This current has no time derivative. There's only x derivative. That's the property I'm emphasizing. Is that the J0 has only x derivative. So it's a space total divergence. J0 is always space total divergence. So therefore, it simply gives you boundary values of that object. In this case phi, but if you have a more general higher dimensional analog, so whatever is the corresponding object here, It gives you the boundary values. So that's another way of seeing that it captures the topological properties. But that is not true. So that which means here that it is the corresponding charge which is the space integral of J0, charge which is Q, which is the space integral of J0, is non-zero only for configurations with non-trivial boundary conditions, non-trivial boundary behavior. In this particular case, it's because these configurations at two boundaries have two values. Whereas for ground states, they have the same value, the charge is 0. And for this one, the boundary behavior of the configuration is different from this one, so the charge is different. This is 1 unit, this is minus 1 unit. Noether current, on the other hand, J0 is not a spatial divergence. Is that clear? I think with this we close the discussion of Sine-Gordon theory. And now I'm going to discuss another field theory, and then we'll try to understand how that theory is related to Sine-Gordon theory. It is dual to Sine-Gordon theory. So now consider another Thirring model. It's a model of fermions with action dx dt in 1 plus 1 dimension, half psi e I d slash psi minus mf fermion mass by 2 psi bar psi minus half g psi bar psi bar gamma mu psi bar gamma mu psi. It's a theory of fermions, and we'll try to argue that this theory of fermions has the same physical content as this theory of bosons. mf psi bar psi, the fermion mass mf, as opposed to m that I introduced there. Gamma mu are the two-dimensional Dirac matrices. Is sigma 1 and gamma 1 is sigma 2. The poly matrices, first two poly matrices, 2 cross 2 matrices. This is a renormalizable theory. You may have heard that for fermion interactions, this theory, this is the mass term, this is an interaction term. This G is the interaction coupling, strength of the interaction, and it has 4 fermion couplings. And normally we don't study 4 fermion theories in 4 dimensions, because in 4 fermion theories in 4 dimensions are not renormalizable. But in 1 plus 1 dimensional they are well behaved. So renormalizable despite 4 fermion interaction. This theory has a global symmetry, global U1 symmetry, since psi goes to psi prime exponential I alpha psi, where alpha is a constant. That's what global means. And associated with this global symmetry, for continuous symmetry, because alpha can be any parameter, continuous parameter, there is a corresponding Noether current. So associated Noether current. Is psi bar gamma mu psi.
One of the gamma matrices should go to -1.
Why should it be -1? Then maybe, I don't know, put an I there. Huh? So all right, let me. Maybe the I times sigma 1. Huh? So anyway, this is the conserved current, and that this has this invariance is very straightforward to see, because psi transforms by exponential I phi, psi bar transforms as exponential minus I phi, I alpha. And alpha is a constant, so it can go across the derivatives. So this is invariant, this is invariant, this is invariant, this is invariant. And associated current, does everybody know how to get an associated current for such symmetry? You've done it several times, right? Is there anybody who doesn't know it? So do this exercise and find out that this is the associated current. Simple way of doing it is that make this space-time dependent, and I make a variation and see how the action varies. That will be divergence of this object times alpha x. That's the associated current. And since the Noether current, it's conserved using equations of motion. So do this also exercise. Exercise d mu j mu is 0 using equations of motion. Corresponding conserved charge q, which is dx of this j0, is dx of psi bar gamma 0 psi, which is dx of psi dagger psi, because psi bar has a gamma 0 in it, so it's gamma 0 square. The gamma 0 square I want 1, so maybe my conventions are somewhat different, otherwise it'll change sign. So all right. Now if I quantize this theory, so quantize this theory. How do I quantize this theory? By look for what is the object which is canonically conjugate momentum to psi. The canonically conjugate momentum to psi is psi dagger. So what I have is psi dagger y psi x anti-commutator is maybe an H cross, and at equal times x and y are space points. This is delta xy, delta y minus x or x minus y. Now let me work out what is the commutator of this charge q with field psi. And that is, charge is now dx commutator of psi dagger y psi y of psi x. Now commutator of psi with psi is 0, because this is the only commutator, anti-commutator that is non-zero. So that is dx of psi y, sorry, this is without, q is dagger, right, psi dagger y psi x. This is anti-commutator. This commutator becomes anti-commutator here by taking out one psi y out. And maybe a sign, because I had to take it across this in order to bring it here, so there's a sign. And replace this object by this and do the integral. Is it clear? Simple enough. So the q commutator of psi is minus h cross times psi. So what does this tell us? Q measures the fermion number or minus q measures fermion number. So fermion number, okay, for a fermion, if I give a fermion number -1, for an anti-fermion I have a fermion number +1, or measures anti-fermion number in my normalizations. So the conserved current that I have here is a fermion number current, and the associated charge is the fermion number of the theory. Now there is one thing we can already notice, which is close to what we saw for the sine-Gordon model, is that the topological charge of the sine-Gordon model at integer values ±1. the fermion number of the massive thinning model has values plus minus 1. Whereas for the Thering model, it's a Noether charge. For Sun-Gordon model, it was a topological charge. So let me write that, is that J mu of beta by 2 pi epsilon mu nu d nu phi of Sine-Gordon theory and J mu of psi bar gamma mu psi of massive Thering model have charges, associated charges, which are set of integers, positive and negative integers. One, and second is that this object is a topological charge or current, and this object is a Noether current. Now, if you complete the quantum theory of massive Thering model, what you discover is that it is exactly equivalent to Sine-Gordon theory if we identify the coupling constant of the Thering model and the coupling constant of the Sine-Gordon model in a particular special way. Identify the coupling constant of beta square h cross by 4 pi of the Sine-Gordon theory as 1 by 1 plus g times h cross pi of massive Thering model. So this is one, if you identify this one. Second, if you identify m square by beta cosine beta of the Sine-Gordon model with mf psi bar psi. In other words, in the quantum Sine-Gordon theory, all properties of this operator are exactly same as the properties of this operator in this Thering model. No, this is full proof. This is full proof, and I will not do the proof here, but you can look up. This was first done by Sidney Coleman. But you can look it up, either Sidney Coleman paper, which is Physical Review D, (11) 1975 is a prehistoric paper. 2088, or look at Raja Raman's book. Chapter 7, Section 3. And if any one of you is feeling enthusiastic enough after reading it and wants to present it in a class, you're welcome. But what is interesting to note here is, then since these two theories, if we make these identifications, have the same properties, which means they describe same physics. So there are two theories describing the same physics. So in this sense, these two theories are dual to each other. Now these two theories are dual to each other. Now what does dual to each other mean? Dual to each other means is that if you look at one, solitons in Sine-Gordon theory, they correspond to massive fermions in massive Thinning model. So the MF that you have here for the fermion is M soliton mass that we had in Sine-Gordon theory. Second, in the solitons in Sine-Gordon theory, we have mesons, which have fluctuations around a ground state, whose mass is what we call small m, and there was alpha times beta in that theory. Those are excitations around a particular ground state, and those are mesons. So mesons in Sine-Gordon theory, which means excitation, perturbative excitations around a ground state, they correspond in the Thinning model to psi bar psi bound states. So going back, this Sine-Gordon soliton of a Sine-Gordon theory is a collective excitation. It's a collective behavior. It's a behavior of the configuration over the whole of space, from x minus infinity to plus infinity in that peg model. Whereas the corresponding object in the fermion theory is described by an elementary excitation. So what is a non-perturbative object in Sine-Gordon theory is an elementary object in the dual theory. The third property now, since the couplings are related like this, if I want to study Sine-Gordon theory in a small coupling area, which means beta is small, that would correspond to the properties of Thinning model for a large coupling, because couplings are related inversely. So a weak coupling properties of Sine-Gordon model are controlled by or describe the strong coupling properties of thinning model. And conversely, the strong coupling properties of Sine-Gordon model are described by weak coupling properties of the thinning model. And that's why weak coupling properties of thinning model, which are elementary fermion excitations, are the solitons here. So another interesting property is that weak coupling properties of Sine-Gordon theory correspond to strong coupling properties of massive thinning model, and strong coupling properties of Sine-Gordon theory correspond to weak coupling properties So number 4 is something we said earlier and I repeat it, is that we have a topologically conserved current here, or a conserved topological current, conserved topological current here, and the corresponding object here is a Noether current with Major's fermion number. I mean, this property that the two theories are dual to each other is a nice property on its own, but it's also an extraordinarily important property, is because most often we know how to do perturbation theory and we don't know how to analyze theories for their strong coupling behaviors. So this gives us a method of understanding the strong coupling behavior of a theory if we know that that theory can also be described as a dual theory wherein the couplings get inversely related to each other. So I can do perturbation theory and thinning model in order to get the non-perturbatory properties of the Sine-Gordon theory and vice versa. So this is a method of probing non-perturbatory structures of field theories if we know for some reason or the other that there is a dual description of the theory. Now this is to be contrasted with the duality we talked earlier in electromagnetic theory with both magnetic and electric charges. There the duality was within the same theory. So that those are self-dual theories. And electric and magnetic charges were related to each other inversely. But here we have two theories which are different and they are related by duality and their couplings are related to each other by inverse. Now we'll try to ask the question, are there theories which are both self-dual as well as dual in the second sense? So they are dual both in the first sense as the second sense. Right? Theories where we'll have elementary excitation in one formulation described with the weak coupling describing, and another formulation we will have a weak coupling of theory which describes the strong coupling properties of the same theory by choosing dual variables. So we'll try to construct examples of those theories in 4 dimensions. We'll also try to construct examples of this variety in four dimensions, which is when the two theories are dual, two distinct theories are dual to each other. And examples are two theories different dual to each other are SU2 n equal to 2 Youngman's theory dual to U1 n equal to 2 Youngman's theory, U1 gauge theory. And self-dual theory is SUN equal to SUN 4-dimensional, n equal to 4 Youngman's theory. That's a self-dual theory which has self-duality of both these kinds. So we'll try to develop those theories now. Meanwhile, please look up Rajaraman's book and try to understand equivalence of Thirring model and Schrodinger-Sine-Gordon model. If you have difficulties, we'll have a session on that later. So we stop early today. I think I'll break now because now next is something else. We'll do 4 dimensions that, and we'll do it next time.